So, let us see how the simple function technique is used to prove this result. Okay. So, let us start. So, we want to show that for every g belonging to L1 of x s nu, integral of g d nu can be represented as integral f g d mu. So, where recall we defined nu of E to be equal to integral of f d mu over E. So, this is the property we want to prove. So, this is the property star we want to prove for every function g. So, as we said, let us first check this property. So, step 1, let us take g is a L1 function. Let us say g is a function which is indicator function of E. Okay. Let us take g as the indicator function of E, E belonging to S. In that case, the integral g d mu, the left hand side, is nothing but nu of E, right, because g is this is the indicator function. So, this integral of nu of E, which by definition is equal to integral chi E of f d mu. Okay. And so, chi E is g. So, this is equal to integral g f d mu. So, what does it says? It says that the required property star holds when g is the indicator function. Okay. And now, let us take a non-negative simple function. So, that is step 2. Let us take g is sigma a I chi E of E I equal to some 1 to n, where E i's belong to S. And our claim is that this property holds for this g also. So, we are saying that next step is to verify that the required property. So, integral of g d nu by definition is equal to integral of sigma a I indicator function of E I d nu. And what is that? By linearity property of the integral, it is sigma I equal to 1 to n of a I, okay, that is a scalar, times nu of E I, okay, because integral of the indicator function is the measure. Okay. So, that is equal to sigma I equal to 1 to n a I, and nu of a I by definition is integral chi E I of f d mu, right. That is the definition of nu of E I is this. So, which I can write it again as sigma I equal to 1 to n, okay, of a I, we can take it out. So, let us, so this is, and again by the linearity property. So, that is integral a I chi E I times f d mu, but this is nothing but my function g. So, this is integral of g f d mu. So, what we are saying that if g is summation a I chi E I, then using linearity property, this is same as integral goes in. So, that is a I integral of the indicator function of E I, that is nu of E I, and nu of E I by definition is integral over E I of f d mu. And again using linearity property of the integral, I can shift it outside. So, it is integral of summation a I chi E I times f d mu, which is g. So, it says, so the required property holds. So, star holds for non-negative simple functions g. So, that is what I said, the simple function technique. And now, let us try to prove it that this property also holds when g is a non-negative measurable function. So, let us look at now g. So, let g on x to be measurable. Then we know by the property of measurable functions implies there exists a sequence S n of non-negative there is sequence S n of non-negative simple measurable functions such that S n increases to the function g. Okay. So, then by Lebesgue by monotone convergence theorem, integral of g d nu with respect to nu must be equal to limit n going to infinity integral S n d nu. But for non-negative simple functions, just now we proved this the star holds, that means this can be written as limit. So, by step 2 I can write this as integral of S n times f d mu. Okay. So, with the integration of a non-negative simple measurable function with respect to nu can be converted into the non-negative simple measurable function multiplied by f d mu. Okay. And now, at this stage we observe that if S n is increasing to g, then S n times f will be increasing to g times f, and all are non-negative simple measurable all are non-negative measurable functions. So, once again monotone convergence theorem is applicable, and this limit is nothing but integral of g f d mu. Okay. That is, so once again we have used so this step was by our step 2, that the property holds for non-negative simple measurable functions. Integral with respect to nu is integral with respect to mu of the product function. And now, once again we are applying monotone convergence theorem. So, first integral of g is equal to limit of integral S n d nu by monotone convergence theorem. And now, by our earlier step, this is equal to integral of S n f d mu, again by monotone convergence theorem it goes back. So, that means, so this implies that star holds for non-negative measurable functions. Okay. And now, let us come to the last part, namely, so let us final step 3 is let g belong to L1 x s nu, g be an integrable function. Now, then what is g equal to? G plus minus g minus, okay, where g plus is a non-negative measurable function, g minus is a non-negative measurable function, and by step 2. So, by step 2 we know that integral g plus d mu is equal to integral of g plus d nu. So, let me write it again, integral g plus d nu is equal to integral g plus of f d mu, and integral of g minus d nu is equal to integral g minus f d mu. So, that is by step 2. And now, because g is L1, so that implies g is equal to g plus g minus. So, g plus is in L1 of nu, and g minus also belongs to L1 of nu, right. A function g is integrable if and only if its positive part and negative parts are integrable. So, that means these quantities, right, they are all finite. These are all finite quantities. So, that means what? And f is non-negative. So, that implies integral of g f d mu is equal to integral of g plus f d mu minus integral g minus f d mu. By definition of the positive part and the negative part of the function g f. F is non-negative. So, the positive part of the function g f is same as g plus times f, and the negative part is nothing but g minus f. And all both of these are finite quantities. Okay. So, that means implies that g f is L1, and by these two this is same as integral of g d nu. So, for a this the step 3 for a g which is integrable, we have deduced that this property is true. So, this is step 3. So, this is what I call the simple function technique. So, let me go back and show you once again what we have done. So, we wanted to show that. So, this is property star, we wanted to show for every function g which is L1. Okay. So, first step is, so this is my step 1, that look at the functions g which are indicator functions. So, I want to verify this for the indicator function g to be the indicator function. So, when g is the indicator function, so this left hand side is integral of over e of the constant function 1. So, this is equal to integral d nu, it's nu of e, which by definition is integral f over e. So, which I can write as integral f e. So, that is true. So, step 1 is to verify the required thing holds for characteristic function, and step 2, by using the property that the integral is linear, okay, we show it is true for every non-negative simple function. So, take g a non-negative simple measurable function and apply. Okay. So, g is equal to integral of non-negative a I indicator function a I and interchange and show it required property holds. So, the step 2 was that the required property holds for non-negative simple simple measurable functions, and then using an application of monotone convergence theorem. So, that is step 3, that if g is a non-negative measurable function, then we know it is a limit of non-negative simple measurable functions, increasing limit. So, an application of monotone convergence theorem together with the earlier step gives us that integral of g d nu is equal to integral of g f d mu. So, that is the next step to show that it holds for non-negative measurable functions. And once that is done, the final step, that it holds for all integrable functions, is via splitting the function g into the positive part minus the negative part. And g integrable means both are integrable, and for each one of them the required claim star holds. So, by putting them together, we get that the required claim holds, property star holds for all functions g. So, which are L1. So, this is what I normally call as the simple function technique. So, while proving results about integrable functions, one uses quite often the simple function technique, and while proving some properties about subsets of sets, recall we had the sigma algebra monotone class theorem technique. So, for proving properties about sets, one uses monotone class sigma algebra monotone class technique, and for proving results about integrals, one normally uses what is called the simple function technique. So, with this we have defined and proved general properties about integral of functions on sigma finite measure spaces. Now, we will specialize this property, this construction when x is real line. So, we want to specialize this thing for the real line. So, let us see what we get. So, we will be looking at the special case when x is real line. The sigma algebra is L, that of Lebesgue measurable sets, and the measure mu will be the lambda, the Lebesgue measure. So, we will be working with the measure space x S mu, which is same as real line, Lebesgue measurable sets and Lebesgue measure. So, the space of all integrable functions on this measure space are L and lambda is called the space of all Lebesgue integrable functions and is also denoted by L 1 of R or L 1 of lambda. So, this is the space of all Lebesgue integrable functions. So, we want to study this space of Lebesgue integrable functions in some more detail. So, let us first agree to call integral f d lambda to be the Lebesgue integral of the function f. So, whenever f is integrable or non-negative, integral f d lambda will be called the Lebesgue integral of f. Sometimes we have to look at functions which are defined on subsets of E. So, for any subset E which is Lebesgue measurable, L 1 of E will denote the space of all integrable functions on the measure space E. So, the underlying set is E. L intersection E is the collection of all Lebesgue measurable sets inside E, and lambda is the Lebesgue measure restricted to subsets of L intersection, the sigma algebra L intersection E. Of particular interest for the time being is going to be the set when E is a closed bounded interval A B. So, we will start looking at the space L 1 of A B, that is the space of all Lebesgue integrable functions defined on the interval closed bounded interval A B, and we also have the space R A B, namely the space of all Riemann integrable functions on A B. Okay. So, we want to compare these two spaces. On one hand, we have got the space of Lebesgue integrable functions on A B. On the other hand, we have got the space of Riemann integrable functions on A B, and we want to see the relation or establish a relationship between the two. And that was one of the starting points for our discussion of this subject, namely the space of Riemann integrable functions had some difficulties, some problems, some drawbacks, and for which we wanted to extend the notion to a larger class, and this is the larger class L 1 of A B. So, what we are going to show is R A B, the space of all Riemann integrable functions, is a subset of L 1 of A B, and the notion of Riemann integral is same as the notion of Lebesgue integral for Riemann integrable functions. So, that is called the relation between the Riemann integral and the Lebesgue integral. So, to be more specific, we want to prove the following theorem, namely if f is defined on a closed bounded interval A B is Riemann integrable function, then f is also Lebesgue integrable, and the Lebesgue integral is same as the Riemann integral of the function f. So, this is what we want to prove. So, let us start looking at how do we prove this. So, the proof of the theorem. So, we are given that the function f belongs to R A B. It is a Riemann integrable function. That means, so let us recall how is the Riemann integral of a function defined. It is defined via limits of upper sums and lower sums of partitions. So, implies there exists a sequence P n of refinement partitions with norm of P n going to 0 as n goes to infinity, partitions n going to infinity with the upper sums of P n's with respect to f, limit of that is same as integral, the Riemann integral of f is same as the limit of the lower sums L P n of f. So, that is the meaning of saying that a function f is Riemann integrable. So, we can find Riemann integrable implies there exists a sequence of partitions P n, which are refinement partitions. Refinement means P n plus 1 is obtained from P n by adding one more point. And norm of these partitions, the maximum length of the subintervals goes to 0, and integrability means that the upper sums and the lower sums both converge to the same value, and that is the Riemann integral of the function f. Okay. So, this is the property of saying that f is Riemann integrable. Okay. So, now from here let us look at what is u p n f upper sum. So, let us write down the partition p n as something. So, let us say p n looks like a. So, interval is a to b. So, a the point x naught less than x 1 less than x n, which is equal to b. So, let us say that is the partition p n. Okay. So, in the picture it will look like here is a, here is b. So, this is x 0, this is x n, and here is x 1, x 2 and so on. Okay. So, to construct the upper sums, what one does? To construct the upper sums, one looks at the maximum value of the function in this interval and the minimum values in this interval. So, let us write m k to be the maximum value of the function in the interval x, say x I minus x k. So, let us say x k minus 1 to x k. I am just trying to make the intervals disjoint maximum in this interval. Okay. Of maximum in this interval, maximum of f of x, maximum in of f of x, and similarly m k, let us write it is the minimum in the interval x k minus 1 to x k of f of x. Only at the end points you have to make it closed, but that is not going to matter much. So, that then we define what is u p n f, that is essentially looks like summation of the maximum value into the indicator function of that subinterval, and the lower sum with respect to p n f looks like summation small m k, the minimum value of the function in that subinterval x k minus 1 and x k. So, let us do one thing. This is upper sums and not, these are not. So, this is not the upper sum. Let us call this, when in the interval x k minus 1 to x k the value is capital M k, let us call that as the function phi k, and when you are taking the minimum value in that interval and summing up, let us call that as psi k. So, these are functions, because they are linear combinations of indicator functions, and the upper sums and lower functions are nothing but the upper sum p n f is nothing but the Riemann integral a to b of phi k x dx, and the lower sum p n f is equal to the integral of Riemann integral of this function psi k of x dx. Okay. That these functions phi k and psi k, which are linear combinations of indicator functions, are in fact non-negative measurable functions on the measure space a b, the interval a b. So, note, so that is the observation that we should note, and then okay. So, let us note down. So, note phi k and psi k okay, are measurable functions, are measurable non-negative are simple measurable functions. Say that phi k is less than or equal to, at every point x is less than or equal to f of x is less than or equal to psi k of x, and as far as the integral is concerned, the integral a to b of f x dx is between the upper sum and the lower sum. So, that is the phi k was a maximum, sorry, so this should be bigger than or equal to like this, because phi k is taken as the supremum. So, this is the upper sum p k of f, and that is bigger than or equal to the upper sum, sorry, bigger than or equal to the lower sum with respect to p k of f. Okay. And in the limit, both of them are converging. So, here is the second observation is that the upper sum with respect to the partition of f is same as, so what was it? So, that was equal to sigma m k into the length of the interval x k minus 1. So, that is the upper sum. Okay. That is also the Riemann integral. Okay. In fact, this is also equal to, okay, so length. So, this is the length of, so you can write this as the length. So, m k times the length of x k minus 1 and x k, which is same as the Lebesgue integral of the function phi k d lambda. So, this is the important observation that we should keep in mind, that the building blocks for Riemann integral, which are these step functions, okay, are also Lebesgue integrable, and the Riemann integral of the step functions phi k and psi k are same as the Lebesgue integrals of phi k and psi k. So, similarly, the lower sum p k f is equal to integral of psi k d lambda. And now, essentially the idea is to put them together. So, because phi k and psi k they are between these two. So, let us look at integral of, so look at the sequence. So, consider the sequence psi k minus phi k minus psi k. Okay. Recall phi k is bigger than f x is less than psi k. So, phi k minus psi k is non-negative for every k, okay, and saying that the upper sums and lower sums converge to the same value is saying that the integral of phi k minus psi k phi k minus psi k d lambda, that goes to 0. Okay. So, that goes to 0. So, because the phi k d lambda is the upper sum, this is the lower sum, and that goes to 0. So, that implies, okay, so that implies that limit. So, that means this implies that the limiting function f is trapped in between. So, that means limit phi k x is equal to limit psi k x, okay, almost everywhere. Why is that? So, that we can deduce from the fact that applying Fatou's lemma. So, to reduce this, look at the limit inferior of phi k minus psi k integral, okay, d lambda will less than or equal to limit inferior of integral phi k minus psi k, and that is 0. So, this is 0. So, that means, and this is, okay, and so this says that integral of a non-negative function is 0. So, the function must be 0 almost everywhere, and that is same as saying this must be 0 almost everywhere, and f is trapped in between. So, that implies that limit phi k x, limit of phi k x is equal to f of x is equal to limit psi k x for almost everywhere x. So, that proves is equal to. So, we are falling short of time. So, that means that the function f is measurable. So, we will continue the proof of this tomorrow in the next lecture. So, our aim is to prove that the space of Riemann integrable functions is inside the space of Lebesgue integrable functions, and the Riemann integral is same as the Lebesgue integral. So, we will continue the proof in the next lecture. Thank you.